So let's look into what is actually needed in these different parts of enabling the full stack integration. So I would like to give a first part, so a first course unit on looking into the room temperature electronics. So here depicted as a rack, which has the wide instruments, the good old QDevil, QDAC, and QBox, which is used to interface to the dilution fridge and the QDAC to tune up and calibrate qubits. Whereas we now can combine that with the quantum machine units, also the OPX that does the real-time quantum control. And that's now what we can do and try and integrate that with software interfacing. So we already have some pulse level software and other tools, and we'll be looking into extending that further to provide more of a full solution that takes also on some advanced capabilities. So what's the whole point of operating a quantum system with room temperature electronics? So first of all, we have the quantum system, but in order to address that, we need to couple it to a measurable classical system. So that is most often done via pulse-based control and readout of the quantum system or qubits, and by that then coupling that back to a classical system. So here, for fun's sake, we've depicted a classical orchestra, but the point with doing that is really that this orchestra has some musicians, and traditionally that's a whole range of different instruments that's used for that. Can be arbitrary waveform generators, digitizers, digital multimeters, lock-in amplifiers, and so forth. So these instruments form like individual musicians in a bigger orchestra that's turning into quite a complex system to operate as we scale up the quantum technologies for quantum computing. So what do we really need then to move away from this complex orchestra that no conductor can really take on conducting over a process where the quantum computing technology scales up to perhaps hundreds of qubits? Well, so we need a seamless integration of all of these capabilities into electronic instruments. So enabling us to do control and read out in an integrated architecture, and preferably doing it with all of that pulse waveform generation and decision making implemented on board, so that we can do that and disseminate some of the readouts from qubits in let's say less than 100 nanoseconds, so we can start to do real-time quantum feedback. So that's where the Quantum Machines OPX platform becomes really handy. So this platform is a fully integrated instrument that has multiple inputs and outputs for doing pulse sequenced control pulses and picking up readout measurements. So that's now all built in an instrument that has a dedicated pulse processor on board, meaning that it can actually do this in real time, less than 100 nanosecond scheme. So apart from that, it's interfaced with a programming and compiling interface, so that the users can easily set things up, and it's then compiled and uploaded to this advanced instrument. So how does it do it? So we have the user on one side, we have the qubit represented by a Bloch sphere on the other side. So in the middle here we have the instrument, the OPX, that has first of all a radio frequency and microwave front end that takes care of all of these pulses, inputting and outputting these. Inside the same instrument, this advanced pulse processor unit that can take care of the real-time processing. So this pulse processor unit takes care of both generating the waveform parametrized. It does also acquire waveforms from the readout measurements. It does then real-time processing of this to actually be able to do a control flow where decisions can be made based on readout inputs and control pulse generation. Moreover, this is done on a multi-input, multiple-output instrument, so you can actually do all that integrated on many qubits, and you can also stack multiple instruments. So it's a scalable platform that we can now take on to multiple qubit devices. So the user sees something that's called QUA, so that's an intuitive quantum programming language. Then we have a dedicated compiler that converts that to machine code, which is loaded into this pulse processor on the instrument. So what can it be used for? So it has been optimized for qubit operations, and here we show an example of silicon MOS quantum dot spin qubits, where you see first of all a very simple code written in the QUA language, which sets up the instrument to perform a full rapid chevron measurement. That's then compiled, loaded to the instrument, and in approximately 4 minutes, the instrument is running this measurement with 100 averages, and you get this data back. So it's optimized also for a workflow for doing these things in the lab. So that's for spin qubits. We have an example here for superconducting transmon qubits, writing a script again that does a full 2D rapid scan with 1,000 averages in approximately 10 minutes. That's one thing we do. The other thing is in this integrated solution is to take the QDevil QDAC2 precision voltage source instrument. So what is this? It's a program and signal generator with 24 channels, stable DC voltages for adjusting gate voltages, but also a high dynamic capability of 1 megasamples per second, enabling it to do scanning and dynamic tuning of gates. So you can see a basic product functionality we have in this product is that it can generate different types of signals, first DC and step functions, sine waves with the sampling capabilities enabling a true sinusoidal waveform up to 30 kilohertz, triangle square waves up to 100 kilohertz, and finally also arbitrary waveform generation, so we can upload arbitrary waveforms with a 1 megasample per second, enabling, roughly speaking, 100 kilohertz bandwidth on these waveforms. So it does that, integrates those capabilities, and includes also a customizable low-pass filtering, so that you can operate that either full bandwidth or with lower bandwidth. So just to illustrate the dynamic response, how fast this can be operated with the 1 megasample sampling rate. Here we show for 1 volt voltage step and for a 20 volt voltage step that it only takes a few microseconds to get that transition happening to within 99%. So a dynamic range of or a dynamic response that enables settling times of a few microseconds. Then secondly, it's very stable, so not only does it provide very high, fast dynamic responses, it's also super stable. So here we've taken measurements at the Danish Metrology Institute to look at a 2-week stability in a temperature-controlled environment. So at the lower point, you see that it was placed in a lab where the temperature fluctuates roughly half a degree, and that means that it's actually staying voltage stable over several weeks to again a few microvolts. So an instrument that can do precision control to a few microvolt precision, and at the same time with microsecond resolution. Interestingly, we can look at noise also with the different filter settings. So we've gone into a great detail of tracing out the noise spectra for the different filter settings, and what you see here is that we are staying under a general level of 20 nanovolts per square root hertz for any frequency higher than 10 hertz, and secondly, if we integrate this noise over a full bandwidth from 1 hertz to 100 kilohertz, this is equal to noise levels of roughly 4 microvolts RMS level. One final feature we'd like to highlight is current sensing also. So this QDAC instrument can sense also the current level on the output as integrated in the output stage of the instrument to a resolution of less than 10 picoamps. So it can also be used to actually perform voltage measurements. So let's put a few use cases out. So quantum dot charge stability diagrams can be traced out. Here you can see actually with utilizing the current sensing, we can get quality plots that resembles the ones that we can get from RF reflectometry on sensor dots. Another aspect is actually compared to data acquisition with the digital multimeter, which takes either minutes or tens of seconds. With the QDAC2, we can actually go into video mode, so we can scan a full 2D map of a charge stability diagram in less than a second. So again, a capability that opens up some really new advanced ways of doing, for example, dynamic tuning and calibration of qubits based on quantum dots. Final use case we'd like to highlight here is this year. We just saw this nice publication from a Japanese team teaming up with Giugiaro here from Delft in doing actually fast universal gate operations on silicon quantum dots, using also again this QDAC2 instrument to tune up these dots in the experiment. So it's just nice to see that there's been some real high quality quantum gate operation happening in qubits using our instruments like this.